Right, this is section C of Unit 7, BTEC Engineering. We're on page 2 of the examples booklet. Now I've skipped C1 for now because C1 is a proposal to solve a problem and C2 is actually solving the problem. Now basically when you're doing your proposal you'll have to look at the standard approach for solving it, and basically that is your proposal in words describing the steps you're going to take. And then solving it is actually C2 doing it. So the problem I'm going to deal with is an engineer is given a sheet of metal 40 centimetres by 30 centimetres, and he's asked the following question, or she: what is the maximum length of time it will take to fill a tank made from the sheet with water at a rate of 2 centimetres cubed per second? Now in this session I'm only going to be dealing with the actual solving of it. I'm not going to deal with the explaining your method except verbally. To get your merits and distinctions you will have to explain your method thoroughly with words in your own words. So make note of the things I say about why we do individual steps. That's what you'll need to be able to do to get the higher grades. Now this is a video rather than lesson, so you may need to pause to take notes. You need to have a thorough explanation, as I've already said, to get those merit and distinction marks. Also, another point is this question could be solved in different ways. However, the problem needs to be solved using calculus, both differentiation and integration, to be able to be awarded the various standards for the assignment. Hence, if you use a different method that doesn't use both differentiation and integration, you will inevitably struggle to pass this assignment. Now, let's say this is an example dealing with how to solve this sort of problem. So we've got a sheet of metal and it's 40 centimetres by 30 centimetres. And what we want to do is to make a tank from it. So a tank is a cuboid shape but with no top lid, top side. So it's an open box, open cuboid. And we want to fill this sheet with water, fill the tank with water. Now, if we want it to take us the maximum length of time it will take to fill it, we're going to need a box with the maximum possible volume because the rate at which we're filling is constant. So first of all, we need to find the maximum volume. Now to create a box out of this sheet, we're going to need to cut out corners. And the corners will have to be squares because what we will do is these outer rectangles will be the flaps, and we would flap it up to create our box. We would attach this side to this side, so they'll have to have the same length. And similarly for each of the squares. So each of these are squares. I'm going to say that they're x by x. Because at the moment we don't know what size squares we would cut out of each corner. Now when we flap it up and make a box, it will be of this shape. You excuse my poor drawing skills. Now the flaps, that means the height will be the x. So it will be x high. But we'll need to know the dimensions of the bottom rectangle, which is illustrated by this rectangle. So we'll need to know the length of the dotted sides. Now if it's 40 centimetres all the way across, and we're cutting x from that side and x from that side, this length will be 40 minus 2x. And so will that. And this length will be a similar sort of idea, 30 all the way, take away x, 30 take away 2x. This corresponds to this side of the tank. Now we need a formula for the volume. To do the volume cuboid, we times length times width times height. So x times 40 minus 2x times 30 minus 2x. So that's our first stage done, completed. We've found a formula for the volume. But we've still got a long way to go. To find the maximum volume, we'll need to use differentiation. And before we can use differentiation, we need to multiply this expression out. So we need to do 40 times, I'm going to start with a quadratic bracket, so 40 times 30, 40 times minus 2x, minus 2x times 30, minus 2x times minus 2x. So doing that, so 40 times 30 is, you should know that, 1,200. 40 times minus 2x is minus 80x. Minus 2x times 30 is minus 60x. Minus 2x times minus 2x, well, minus 2 times minus 2 is plus 4. X times x is x squared. And that multiplies out the brackets. Collect the like terms. So start with x squared, we've got 4x squared. Then collect the x's, minus 80x minus 60x is minus 140x. And only one number term, plus 1200. And then to finish off the multiplying out, we times through by the x. So 4x cubed minus 140x squared plus 1200 times x. So we've got a multiplied out expression for the volume. We then need to differentiate. So to differentiate to dv by dx. Now the process of differentiating a polynomial, we times by the power, so it's 3 times 4. We take 1 off the power, 3 take away 1. Next term we times by the power, 2 times 140. Take 1 off the power, 2 take away 1. And any number times x term differentiates to just the number, so 1,200. Simplifying, we get 12, 3 times 4 is 12, 3 take away 1 is 2, so 12x squared. 2 times 140 is 280. 2 take away 1 is 1, we don't need to write powers of 1. Plus 1,200. And for a maximum, or any stationary point, the v by dx would be equal to 0. So we need to solve that quadratic, 12x squared minus 280x plus 1,200 equals 0. And we can use the silver calculators to help us with this. So we can use a mode on the calculator. So if we do mode 5 for equation, we get 4 options. The quadratic mode is 3. And if you do that, you get a grid, A, B, C. And we need to fill in values for A, B, C by typing in the number and pressing equals when the relevant column is highlighted. Now the A, B and C depend on the quadratic we've got at this stage. So our A is the 12. Our B is the minus 280, don't forget the minus, that's crucial. And the C is the 1,200. So whatever your numbers are at those stages, that's what you would stick in for A, B and C, by sticking in the number and pressing equals. So 12 equals minus 280 equals 1,200 equals. Once they're all in, if I then press equals again, it starts giving me answers for x1 and x2. On the decimal version, so I might have to press the SD button to make that happen. It's equals again. We get an x2 value. So x1 and x2 are 2 possible x values that solve that equation. Now, going back to the situation, These are basically the length of the squares that we're cutting out. If we had 17.6, we would cut more than halfway from that edge from that side, more than halfway from that side, so our cut squares will overlap, which is not possible in real life. So the top number is not possible. It is, however, possible to cut 5.65 centimetres and so on from each side. Excuse me. So we've got our x value, what we're cutting from each side. We then need to check whether that gives us a maximum volume or a minimum volume, or basically just the zero gradient for this formula. And to check that, we need to do what's called the second derivative test. So we need, and actually before we do that, we need to switch our calculator mode back to normal. So back to normal is mode 1. To do that on my calculator, mode 1 sets me back to normal. And then proving it's a maximum, I need to get my div by dx formula back. So div by dx is 12x squared minus 280x plus 1200. We need to differentiate again, so the notation is d2v over dx squared for a second derivative. Same rules, multiply by the power, so 2 times 12, subtract 1 from the power, 2 take away 1, minus 280x. We just take the number in front of the x, and constant 1200 is just a number that differentiates to 0. Simplifying, 2 times 12 is 24, 2 take away 1 is 1, we don't need to provide powers of 1, so 24x minus 280. We then stick our x2 value in. So 24 times minus 5.65 and so on, minus 280. So doing that in the calculator, we get minus 144.222051, which is less than 0. So the point of the second derivative test is that if it's less than 0, it's a maximum. So we can write therefore maximum volume. So we found that our x value corresponds to maximum volume. We haven't actually found the volume yet, so we go back to our V formula. And we stick our x value in, so 5.65 74 dot dot, I'm going to write dot dot dot, but when we're calculating it we don't want to be rounding at this stage. 40 minus 2 times 5.6574 dot dot dot, 30 minus 2 times 5.6574 dot dot dot. Calculate all that and we'll have our maximum volume. So stick it into the calculator. Our maximum volume is 3032 and 302466. Well, that's just the maximum volume. We still haven't found the maximum length of time it will take to fill the tank. Now we're told that the rate it's going in is 2 centimetres cubed per second. So that means that the V by the T is equal to 2. We then need to integrate to get the volume in terms of time. So if we've got a constant, we just add the T on the end. So V is equal to 2T plus C. But since when T equals 0, when we start, there's nothing been filled in, so the volume will be 0. That means that the C will be 0, so the formula is V equals 2 times T. Now we've got a volume and we want to find the time. So rearranging that equation, T will equal V divided by 2. So T equals 3032. So from here, 0.302466 divided by 2. Which is 1516.151233 seconds. Isn't a particularly useful measurement, so dividing by 60 will tell us how many minutes, because there's 60 seconds in a minute. So it's 3 significant figures, 25.3 minutes. So bear in mind, as I illustrate from the start, just solving it is pass-worthy, as long as you've got a decent proposal where you outline the different processes that you found a formula for the volume, used calculus to find the maximum volume, use the second derivative test to check it was a maximum, we used integration to find a formula for volume in terms of time, and then used our maximum volume to find the corresponding time. You need all that in your proposal, and solving this to get the pass criteria, to get the merit and distinction criteria, explaining your method, explaining what you're doing and why the quality of your response will determine what grade you get. So best of luck.